I recently fell into a rabbit hole of triangulation or signal localization, whether that signal be a cell phone signal like a radio wave or a sound wave such as from a gunshot. And one discovery keeps leading to the next, which leads to the next. And so after posting one of my videos about trying to find the location of a sniper by using different microphones and some trigonometry, YouTube AI talked about how the speed of sound varies according to temperature and wind, so I did a separate video on that. But something I discovered was if you have, let's say, 3 microphones here arranged at a right angle, so we have one high, one low, and then one off to the right. If you have a variation in the speed of sound from either temperature or wind, then it depends on the direction of that sound wave compared to the arrangement of your microphones. So for example, we have 2 microphones right here. If that sound wave comes in line with these microphones, so it's at 0 degrees, then you will have a large error rate or a large error in your angle. But if that sound wave hits 2 microphones perpendicularly, then you'll have no error rate, which makes sense because if you have a sound wave that is moving, say, twice the speed according to your calculations or half the speed from what you calculated, that sound wave is going to hit both microphones simultaneously. So you'll have a 0 amount of time between that sound wave hitting both microphones, and you'll still have no error, meaning you know that that sound, for example, is coming directly from the right or directly from the left. Also, as I've said in my other videos, I'm not an expert in any of this stuff, meaning the technology that's used or math or whatever. I'm just using simple high school trig. And what you can do to make this more intuitive, instead of thinking about the technology and the number of milliseconds that it takes for sound to travel from one microphone to the next, you could actually make this very intuitive and just pretend it's some people out floating on their boats in the ocean getting ready to watch a volcano on an island explode. If there's a volcano that's about to explode at a certain location out here, and there's one boat here, and there's another boat that's 2 miles behind the first boat, sound travels at approximately 1 mile every 5 seconds. So that means the people in this other boat will hear that sound 10 seconds later, approximately. But if that sound is perpendicular to both microphones, then that means they will both hear the sound simultaneously. And if one boat or one microphone hears the sound, say 5 seconds later instead of 10 seconds later, then that means the volcano is at a 60-degree angle relative to those boats or microphones. And that's because the cosine of 60 is 1/2. So for me at least, it makes it much more intuitive if I just don't think about the technology or the milliseconds and just pretend it's some people out floating around in their boats getting ready to watch a volcano make a really loud boom a really long distance away. So what I'm going to do in this video is calculate the error rates if we misjudge the speed of sound. And I'm going to show that the closer that sound wave gets to perpendicular to hitting those microphones, then the less error you will have. And I'm going to try to, basically what I was trying to do is find the logic and a mathematical formula to explain this. So here we go. We have 2 microphones here, one here and here. That's a vertical array, or you could say actually this is pointing north, so up is north. And then we have this one and this one, so this one points east and west. So we have these 2 mics that point north and south, and we have 2 mics that point east and west, even though this one microphone right here actually is both the south microphone and the west microphone. So let's say we have these 2 microphones arranged right here, and there is 1 unit of time between them. Say it's 1 millisecond, or it could actually be a whole second. Maybe these 2 microphones are about 300 meters apart. So a sound wave comes along, hits one microphone right here, and then 1 millisecond later or 1 second later hits this microphone. So you'll know that sound wave is coming, or the source of that sound is coming directly from the east. And likewise, that sound wave will hit both of these microphones simultaneously, so you know it's coming directly from the east because it hit the east microphone first. But now let's say the source of the sound is off here at an angle at 20 degrees. It'll come up, hit this microphone right here, and instead of 1 second later, it'll be 0.94 seconds later. You can just use simple trig to find out that is a 20-degree angle. And if alpha right here is 20, then that means beta right here has to be 70. If this angle right here is beta, then a parallel angle will also be beta right here, which makes this one alpha. You can see my other video on the interior angles of a triangle and how they have to add up to 180 degrees if you want. Or you could use opposite angles here, or vertical angles. The source of the sound will be at a right angle compared to the sound wave. And so if this angle right here is beta, this one has to be beta. This forms a 90-degree angle because it's the angle between the origin of the sound and the sound wave. So that means this has to be alpha, which means that one has to be beta. So what I'm going to do is increase the speed of sound by 10%. So it'll go from 1 to 1.1. And I just wrote here, if the speed of sound, Mach or whatever, decreases so that the adjacent leg is greater than 1, then you can either do the calculations for the speed of sound compared to temperature, because as the temperature gets colder, you'll have a decreased speed of sound right there. Or you can just use the microphones that are closest to perpendicular to the source of sound. The logic on this is you cannot have an adjacent leg of your triangle being longer than your hypotenuse. What this shows is, in reality, these arrays that they sell on the market to militaries or whatever, there's actually a bunch of different microphones. So basically, if you were to have a whole sphere of microphones, then whichever microphone gets hit first will be the general direction from which the shot came. But after that sound wave hits the first microphone, it's also going to hit a second microphone. So say it hits this one first and then hits that one second. What you need to do is choose the two microphones that are closest to perpendicular to the origin of the sound. And thus it'll be the two microphones that have the least amount of time difference between them. And what we are interested in here for the calculations is we want the amount of time it takes for the sound wave to hit the second microphone after it hits the first microphone. So if we use this array right here, where the origin of the sound is closer to parallel to this microphone array of this mic and this mic, then that'll be 0.94 seconds or milliseconds, whatever. But if we use this microphone array right here, then after that sound wave hits one, we only have 0.34 milliseconds until it hits the other, which means this array will give you a more accurate reading or a more accurate angle. And I'm going to show why in this video. I'm going to show how I get my numbers here. Distance over time equals velocity, so distance over velocity equals time. This is the new distance, or d sub n, for the new distance of the leg of the triangle. Let's take our 0.94 right here, divide it by the velocity of sound, which will be 1.1, because we sped up sound 10%. We get the new distance, which will be 0.85. So we turn this 0.94 into 0.85, and then we recalculate our angle. And the purpose of doing this is I'm going to show what happens if you have a 10% error rate, either in the speed of sound or the distance between your microphones or whatever. Anyways, take the arc cos of 0.85 and you get 31.8 degrees. Take 31.8 minus 20 and we get 11.8 degrees. So that means our angle is off by 11.8 degrees. Let's find out how that translates into distance right here using the arc of a circle. Theta over 360 equals arc over circ. See my other videos on this topic for all the details. We get an arc length of 206 meters right there. So that means we missed the mark by about 200 meters. Now I'm going to show what happens if we use these two microphones right here that are closer to perpendicular to the origin of the sound. And by the way, here I said that you want these two lines to be measurably parallel. So the origin of the sound has to be so far away that these two lines are basically parallel to each other. You can see my other video for the details on that. I'm going to do the same calculations for the two microphones arranged in a north-south orientation. Distance over velocity equals your time, which equals the new distance of our leg of the triangle right here. So we take 0.34 divided by 1.1, we get 0.31. Take the arc sine of that, because here's alpha. We want this length right here. We get 2 degrees. Take degree over 360 degrees equals arc over circ, and we get an arc of 35 meters. So even in this unrealistic scenario where the speed of sound was increased by 10%, or maybe we had a 10% error in the distance between our microphones or something, because we used two microphones that are closer to perpendicular to the origin of the sound, we only missed the mark by 35 meters. Now I'm going to show a really extreme case where the sound wave comes in virtually parallel to one microphone array and virtually perpendicular to the other one. Actually, before I do that, I'm going to show the calculations and the logic on this. Distance over velocity equals time, which is the new distance as I explained earlier. So distance over 1.1 equals the new distance. In other words, this is distance over new distance equals 1.1. I just rearranged the equation. Take both of these to the negative first power. We end up with new distance over distance equals 1 over 1.1. So the new distance is 91% of the original distance. In both of these situations here, the new distance that I calculated for these legs of the triangle, they are 91% of the length of the original length of that leg. So I just did this to show that the percent change is the same for both of them. So I just said here, whether we're dealing with the long leg of the triangle or the short leg of the triangle, they are both shortened to 91% of their original length. Yet when we use this triangle right here, where the sound wave is closer to perpendicular, our error rate is much, much less. And that is because the angle theta is determined by ratios. We have the ratios of your opposite, your adjacent, and your hypotenuse legs of the triangle. So I took the 0.94, which was the original length or the actual length, and then the measured length is 0.85. That comes out to be 0.09. Divide that by the length of the hypotenuse, which is 1 right there. We get a 9% change. Do the same thing for the microphone array where the sound was closer to perpendicular, and we have 0.34 for the actual length, 0.31 for the measured length. That gives us 0.03 divided by 1 for the length of the hypotenuse, and we only have a 3% error. So what we're looking at here, even though both legs of these triangles are changed and they're both shortened to 91% of their original length, they lose the same relative length, but the leg on this triangle right here loses much less absolute length. So we're looking at the difference between relative and absolute change. To understand things in math and physics and science, it often helps to look at extreme examples. So that's what I'm going to do right here. I'm going to take a triangle with the opposite leg of 1, hypotenuse of 100, and then the adjacent leg will be 99.99. This gives us an angle of 0.57 degrees. In other words, this sound wave is hitting these two microphones here at almost 0 degrees. And it's hitting these two microphones here at almost 90 degrees or almost perpendicular. And let's look at our error rates. These are just the calculations for the triangle. What I'm going to do is double the speed of sound. So I just wrote Mach 2 here. That's technically probably not the most accurate way to phrase that, because Mach is a speed relative to the speed of sound. So when you increase the speed of sound or you double it, you're still getting a Mach 1. That's still the speed of sound. But oh well, it's just a quick abbreviation or shorthand that I made up. So what this is going to show is that my calculations are going to be absolutely way off, because I'm calculating the speed of sound to be half of what it really is. So this should actually cause a huge error rate. But I'm going to show that when you use the two microphones that are almost perpendicular to the origin of sound, you'll have almost no error rate. And right here I just said distance over velocity equals the new distance or the measured distance, which is also time. Time and distance can actually be used synonymously. For example, if you're going down the highway at 60 miles per hour and something is 60 miles away, people might say that that location is 60 miles away, or they might say it is 1 hour away. We have here that the distance of the cosine leg is 99.99. Divide that by 2 because the speed of sound has increased. So this means that leg is now 50 instead of 100 approximately. Take the arc cos 50 over 100 right there to get your angle. Now we have a 60-degree angle, and that is way off compared to our 0.57 degree angle. That's the actual angle. What we have done is kept the hypotenuse at 100, but we have now shortened the cosine. Sorry, we kept the hypotenuse at 100, but I've now shortened the cosine or adjacent leg to half. So this is going to cause a very steep angle. So we went from 0.57 degrees to 60 degrees when you take the arc cos of 50 over 100. So we missed the mark by about 60 degrees. In other words, our measurements are worthless. And that is because I used the microphone array that is almost parallel to the source of sound. So when I use cos theta, it decreases the leg of the triangle by 1/2 right there. And I take degree over 360 equals arc over circ. And we end up being a kilometer off, 1,030 meters. So we missed the mark by a kilometer. Now I'm going to use the 2 microphones that are virtually perpendicular to the source of sound, which means I'm going to use the opposite leg of this triangle, that is 1 instead of the adjacent leg, which was 99.99. It still loses the same relative length, so it still gets cut in half because sound is traveling twice as fast, so it'll cover that distance in half the time. So let's take the arc sine of 0.5 over 100. We get 0.29 degrees as our measured angle compared to 0.57 degrees, which is the actual angle. That means we're only 0.28 degrees off. And plug that into the equation of a degree over 360 equals arc over circ. We get an arc of 5 meters. This means we only missed the mark by 5 meters, even though our measurements were way, way off. But this shows that by having a large number of microphones, so that 2 microphones will always be virtually perpendicular to the source of sound, this will greatly mitigate any errors. And again, this comes down to comparing your new length to the length of your hypotenuse. The new length will be 0.5 instead of 1. Divide that by 100, we end up with 0.5%. So our angle has barely changed.